Hey guys, today we'll be talking about improper integrals and specifically type 1 of improper integrals. So they're called integrals with infinite interval. So what I'm talking about is there's something like this. So they are continuous, so the graph does not break, so it's not like this or it's not like it breaks at a certain point, but the thing is that the bound, the upper and the lower bound, one of them or both of them are not properly defined, so it's indeterminate. Yeah, so there are two types of improper integrals. Oh wait, let me define what improper integrals are. So when you talk about improper integrals, they are the integrals that cover an unbounded, unlimited area. So they don't have any restriction, and therefore they're unbounded. And in this video, we'll be talking about type 1. There are two types. This is the first type. The second one is discontinuous integral. We'll be talking about that in the next video. But for this video, we'll be talking about integral with infinite interval. So something like this, as I mentioned, okay? So, yep, let's define this. No fixed bounds. Okay, so the reason I have this graph over here is, so the blue graph represents the function 1 over x square, and the red one represents the function g of x, let's say 1 over x. The graph is not very different. Both of them seem to be having similar curve, and then seem to be, kind of very close to each other after a certain point, seem to be headed towards the x-axis, right? But let's use integrals to find if that's the case. So let's see f of x is equal to, let's start with g of x. Let's start with 1 over x and then move our way up. So g of x is equal to 1 over x. Okay, so it is the red one, the red curve. So let's start with 1, goes on till infinity, 1 over x dx. So our starting point would be, right around here. So let me make a straight line from this. Yep, so this is the point where we are starting our integral. So what we are trying to find is the area under the curve, the red one, to start off, up until infinity, to see if it really converges to the x-axis or not. It looks like it does. See, it started way high up here, and then it seems like converging, but let's see if that's the case. So let me try to be quick. Yeah, and whenever you're solving improper integrals, you use a variable, something like, let's say, p, to replace something, replace the infinity sign, because it's indeterminate. We don't know what it exactly means. So we are trying to replace it with a variable, 1 over x dx is equal to, what is the integral of 1 over x dx? It's one of the simplest ones we've dealt with. There is ln absolute sine x, and since this has bounds, okay, so now what we do, the next step is make use of the bounds. Oops, this better. So ln p minus ln1, and the one of the features of ln logarithm is if we have ln a minus ln b, then you can write it as ln a over b, or simply, since it's 1, ln p is equal to limit p tends to infinity ln p. It's the same thing, but yeah, I guess I could have just skipped this line. It's the same thing anyway. So now if you think of it, and if you've ever looked at the graph of ln log to the base e, then you must have noticed that when the value of ln to the power to the the ln in the oh god my bad. So the ln of infinity is infinity. If you look at the curve, it's something like this, right? It might not be accurate, but it's something like this. And as you move towards your right, towards the infinity, the value keeps on increasing. We don't know what the value is. It does not converge. Therefore, this would be your answer. As p tends to infinity, the value of this is also infinity. We don't know what that is. No finite number. Now let's go see the other one, 1 over x squared. They look similar. Let's see if this one converges. The first one did not. So will this? I don't know. Let's see. We do the same thing. We introduce a variable. Let's say m tends to infinity 1 m x squared. What is the integral or antiderivative of 1 over x squared? Let's do this x. Now you just use the formula that probably all of you know. It is limit m tends to infinity as it is. What's the formula? It is x to the power n plus 1 over n plus 1. In case you had already forgotten. Minus 2 plus 1 m1 is equal to limit m tends to infinity x minus 1 minus 1. Alright, so it is limit m tends to infinity minus. Okay, now let's make use of the bounds. So it'll be minus 1 over m minus minus plus 1 over 1. So is equal to limit m tends to infinity minus m plus 1. So now let's insert the value of m, and as we insert the value of m, what do we get? This tends to be 0 because a number over infinity is 0. It's a very, very, very small number. Therefore, limit m one is equal to 1 square unit. Since it is area, it would be square unit. So the blue line, the blue curve, when you start at point 1 and when you go all the way to infinity, sorry if my thermostat's making a lot of noise. Anyway, if it goes all the way to infinity, the blue curve, it would be incorrect to say line. So blue curve converges, and the total area it encompasses, bounds, is 1 square unit. Whereas 1 over x, the function 1 over x, when you integrate it from 1 to infinity, it seems to be similar. The shape seems to be similar, and the red curve seems to be converging, but no, it does not converge, and therefore its area is infinity. You don't know what that is. So yeah, this is the first part of improper integrals. This is type 1. I gave you an example to show how we solve it, and to see if things converge or not. And in the next video I'll be talking about discontinuous integral, where the bounds will be finite but the function will not be continuous. There'll be gaps in between. So yeah, I hope you had a fun time learning this, and hope to see you in my next videos. Thank you.